On Tuesday, we started talking about radioactivity, that spontaneous, that natural, that random process whereby a nucleus decays into something else. By spontaneous, by natural, by random, we mean that it's a process that happens on its own and when it wants to happen. We don't control whether it happens or not, and we don't control when it happens. It is purely natural. Now, we talked about 4 types of radioactivity. We talked about alpha decay, beta negative decay, beta positive decay, and gamma decay. If we have an unstable nucleus, and it can be unstable for a number of reasons, if we have an unstable nucleus, it may decay in order to become more stable. And one of the things that can happen to it as it does that is that it can give off what we call an alpha particle, which is a particle that consists of 2 protons and 2 neutrons. It is exactly the same, chemically indistinguishable from a helium nucleus. Don't get that mixed up with helium atoms, the helium that you breathe in from a balloon to make your voice turn high, because I was about to say it's not the same thing. It is and it isn't the same thing. The helium atoms that you breathe in have the electrons orbiting around it, and that's not such a big deal because now we're not talking about ionizing radiation. The helium atoms don't ionize things. Helium nuclei ionize things. Beta negative. A beta negative particle that's released as a result of an unstable nucleus trying to become more stable looks like this. 0, -1, beta. Well, that's exactly the same thing as an electron. So sometimes we actually write it as 0 -1 e. Beta positive, almost the same, except we're not talking about an electron that's emitted. Rather, we're talking about an anti-electron. Or what's the name for an anti-electron? A positron. We're still going to make the symbol E. If we made it a P, that would be a proton as opposed to a positron. But we're going to put a little +1 in front of it so that we recognize that it's not an electron, but rather the antiparticle of an electron, the positron. Gamma rays. Gamma is just 0, 0, so of course that just means that there's no protons, no neutrons, no electrons, no positrons, nothing that's matter or antimatter, rather it's just energy. This is energy, pure energy, EMR, electromagnetic radiation. This is matter because it has mass. This is matter because it has mass. This is antimatter, which is exactly the same as matter in almost every regard except for charge. An anti-electron or positron is identical in every regard except for charge to an electron. So it's not like it's a proton. It's not a proton. A proton has a mass of 10 to the minus 27 kilograms. This is 10 to the minus 31, just like an electron, except that its charge is positive. So we call it antimatter, the antiparticle of an electron. Now, let's spend a couple minutes reviewing what caused the alpha decay, this alpha particle, this helium nucleus to break off, and the beta particle, and so on. Remember, the alpha decay occurred as a result of having too many protons. You got big nuclei with big atomic numbers, and you have too many protons relative to the number of neutrons. Protons repel each other. And so there's an electrostatic, an electric repulsive force that acts between proton and proton. There is an attractive force that acts between proton and proton and neutron, called the strong nuclear force. If the attractive force wins, then the nucleus is stable. If the repulsive force wins, then the nucleus wants to break apart. It's kind of like if we got 25 people together in this room and we all held hands and pulled each other towards each other, then we would stay together. But if we had 25 people in this room and we started pushing each other away, then the circle of people would break apart. When the repulsive force wins, the nucleus breaks apart. So we're going to say that this occurs when the repulsive force, which is that electric force acting between proton and proton, is bigger than the attractive force that acts between proton-neutron, neutron-neutron, proton-proton, that strong nuclear force. So when this happens, sometimes an alpha particle or a helium nucleus will break off in an attempt to make our ratio better, in an attempt to make a more favorable, attractive, strong nuclear force. The example that I gave you in this yesterday was platinum, 192, with atomic number of 78. 78 protons, and what is that, 114 neutrons, 192 minus 78. Okay, it undergoes alpha decay, so we'd say that it results in an alpha particle. The parent nucleus is platinum. Okay, that parent nucleus breaks apart to become more stable by releasing an alpha particle, and we're left with a daughter nucleus, or a nucleus is produced, that would be 188. 4 plus 188 is 192. 2 plus 76 is 78. And I think that worked out to be OS. I don't remember those numbers, right? That's why I wrote them down on the board over here so that I would just be able to cheat and look over there, right? Where do you cheat to find what atomic number 76 is? On your periodic table, right? That's why you have a periodic table on your data sheet. By the way, is there anything else produced there? Yeah? No, not one of those V things. Yeah. With alpha decay, that's it. That's the end of the line. That's the end of the line. Now, that's not to say that osmium I think it's called, isn't radioactive. It could in itself be radioactive. In fact, it's quite likely that it will be radioactive. So it could undergo a beta decay, which would release a neutrino, or it could undergo beta negative or whatever. But in this step of it, we're done. Okay, in this step, we're left with an alpha particle in OS. Beta negative decay occurs if you have too many neutrons, but for a completely different reason. It has nothing to do with the force of repulsion or attraction acting. Rather, it has everything to do with the energy. We have too many neutrons. It's energetically unstable. It just doesn't like the state that it's in. Okay, it's like having, you have 4 Red Bulls. You're kind of jittery. You're a little bit unstable because you had too much caffeine. Okay? So that's kind of where we are here too. Is this beta particle, or sorry, this nucleus that's unstable is unstable because it's in an energetically unfavorable state. Now, if we have too many neutrons, and that's what's causing it to become energetically unfavorable, just like you having 4 Red Bulls causes you to become energetically unfavorable, then we have to get rid of 1 neutron. But we don't get rid of a neutron by kicking it out of the nucleus, because the nucleus is a little club. And there's protons and neutrons in the nucleus. And the nucleus likes protons and neutrons, so it doesn't want to just kick out a neutron or a proton. Rather, what it does is changes a neutron into a what? A proton. Is that it? And an electron. We have to have the electron as well, otherwise the law of conservation of charge would be violated. Neutral would be going to positive, which can't happen. The example of this that we have is carbon-14. It undergoes beta negative decay. Get rid of a neutron, change into a proton. 14 plus 0 is 14, minus 1 plus 7 equals 14. And that's nitrogen. So you can see here now, look at this bottom number here. We had 6 protons, now we got 7 protons. We had 8 neutrons, now we have 7 neutrons. 1 less neutron, 1 more proton. And then, of course, we've got this beta particle that gets kicked out. Now, Spencer, what else we got here? Yeah, this would be an antineutrino, or that little V with a line on top of it. Beta positive occurs once again because we have too many protons, but not for the same reason as alpha decay occurred. We get too many protons here, and that leaves, in certain cases, the nucleus to be energetically unstable. So we get too many protons, stands to reason that we're going to get rid of a proton. But we don't just kick it out because the nucleus likes protons and neutrons. So what we do is change it. What do we change the proton into? A neutron. But what else? Because that's not enough. Otherwise, the law of conservation of charge would be violated. What else do we change it into? A positron, right, a positron. Now, an example of this would be carbon-10 undergoing beta-positive decay. What are we left with? 0 plus 10, 1 plus 5. 1 plus 5 equals 6. Be careful with this, eh? This is a really, really common mistake, mixing these up. Okay, especially this one. Minus 1 plus 7, not minus 1 plus 5. Okay? I bet, if you get a question like this on a test, I bet 20% of you are going to put a 5 right there instead of a 7. And you can be sure that if it's multiple choice, that option will be there, because they're going to recognize that that's a common mistake that people make. 5, I think, is boron, isn't it? B? What else we got there? Spencer, what else we got? Yeah, we just got a neutrino there. Good. And finally, gamma. This is kind of the easier one because it's just the result of something that's already happened. It's a byproduct or an afterthought of something that's already happened. The nucleus after beta decay or alpha decay is left in an excited state. Doesn't want to be in an excited state, though. So it goes back down to its normal state by giving off energy. And it gives off energy in the form of a photon, a gamma ray photon. Matter has been converted to energy. All right. Let's pick up in the last two columns where we left off yesterday. When we talk about penetrating power, we're talking about the ability of this ionizing radiation to penetrate matter, to go through matter. When we talk about ionization power, or ionizing power, we're talking about the ability of this ionizing radiation to turn atoms, neutral things, into ions. And we talked about the issue with that yesterday, right? Ionizing radiation turns atoms into ions, and then we got charges floating around, which causes reactions that aren't supposed to take place, and which can lead to all kinds of undesirable effects. Alpha particles have a very low penetrating power. Very low penetrating power. In fact, it's so low that if you one day just got so mad with me and decided to bring your alpha gun in and attack me with your alpha gun, you walk up to me and you say, Mr. Dickie, I've had enough. I got my alpha gun. And you know what I would say to you? Bring it on. And I would hold up my little alpha shield like this and protect myself with a piece of paper. The penetrating power of alpha particles is such that it's going to be stopped by 1 or 2 sheets of paper. My clothes will stop alpha particles. It's a very, very low penetrating power. Now, gamma rays, on the other hand, let's scroll down there. Gamma rays, on the other hand, have a very high penetrating power. We're talking about several centimeters of lead. When you go to the dentist and get x-rays, we're not talking about gamma rays, but we're talking about the next closest thing to gamma rays, right? X-rays. They always put this lead vest over you, a couple centimeters of lead. Right? Why do they do that? To protect the rest of your body from these extra x-rays, right? Well, they do that. They require a couple centimeters of lead to do that for x-rays. You can imagine for gamma rays, it would require even more. Okay, gamma rays have a very, very high penetrating power. You need several centimeters of lead in order to stop it. Beta particles, well, they're kind of the fence sitters. They're kind of in the middle. We'll call it intermediate or medium. They can't decide whether they want to penetrate matter a lot or a little. By the way, alpha particles have such a low penetrating power because of their size. Like they're so big compared to electrons, and they're so big compared to, well, gamma rays don't even have any mass or size, right? So stands to reason that gamma rays will penetrate matter the most, and alpha particles will penetrate matter the least. The ability to ionize matter, though, is exactly the opposite. Gamma rays, although they have a very, very high penetrating power, they have a low ionizing power. That doesn't mean they can't ionize matter. They do. We use gamma rays in the treatment of cancers. We talk about radiation therapy. That's gamma rays that hospitals use. They have a radioactive source which generates either alpha or beta, and then as a byproduct of that generates gamma. The hospitals take the gamma rays and focus them through your body in an attempt to kill cancer cells. Gamma rays can ionize atoms. They do. And that's why they're effective in killing cancer cells. But they have a lower penetrating power, ionizing power, compared to the other ones, compared to alpha and beta. Alpha, although it has the lowest penetrating power, has the highest ionizing potential, the ability to ionize matter. So they have a tough time getting into your body because of the low penetrating power, but if they do, watch out. And lastly, beta, otherwise known as our fence sitters, they have an intermediate or medium ability to ionize matter as well, somewhere in the middle, in between gamma rays and alpha particles. The real issue here is not so much being exposed to alpha or beta. The real issue here is being exposed to something that produces alpha and beta and ingesting that. If the soil is contaminated by radioactive material, then you may eat plants that are contaminated with radioactive nuclei, which will decay in your body. Not penetrate into your body, but decay once they're in. Or you may drink a liquid like water that's been contaminated with radioactive material that will decay once it's in your body. That's the bigger issue than being exposed to decaying particles producing alpha particles. Does that make sense? We've got a couple example questions for you that are going to provide us with more examples. A couple examples we've already done for alpha decay, beta negative, beta positive. Just what we call transmutation equations to describe the reactions that are taking place. Transmutation, by the way, just means the conversion of one element to another. Now, you might confuse that with radioactivity, because didn't we say radioactivity is the conversion of one element to another? No, we said radioactivity is the decay of a nucleus. Transmutation is the conversion from one element to the other. So transmutation can occur by radioactivity. Radioactivity can cause something to be transformed into something else. But there's a number of other processes that can cause some nucleus to be transformed into something else as well. Radioactivity is only one example of transmutation. So for this transmutation equation, it is radioactivity, and it's specifically alpha decay. So let's write this down. We got 22688 radium. This is our parent nucleus. It's decaying to an alpha particle. You could write that 42 alpha or 42 He. It's the same thing. It's on the right-hand side because it's made. It's produced. We start with radium. We end with an alpha particle and something else. What is that something else? Well, we'd say 4 plus 222 equals 226. 2 plus 86 gives me 88. How do we find out what atomic number 86 is? Periodic table. I think it's radon, isn't it? Rn. Anything else produced there? Spencer? No, that's it. Second one says write the nuclear equation for the transmutation of a radioactive isotope lead-214 undergoing beta negative decay. By the way, I specify here that it's beta negative decay, but if it doesn't specify, you can assume it means beta negative. Okay? It says beta negative, that's what it means. It says beta positive, that's what it means, beta positive. If it just says beta, then assume beta negative. So we got lead-214 undergoing beta negative decay, 0 minus 1 beta, or we could say 0 minus 1 E. It's a product. 0 plus 214 minus 1 plus 8 83, I mean, sorry, 83. 83, which is bismuth, I think, isn't it? Bismuth is our daughter nucleus, lead is our parent nucleus. Anything else there? Yeah, what else? Anti-neutrino goes with negative, neutrino goes with positive, so that's right. It's a V with a little line over it. 3 says write the nuclear equation for the transmutation of Mg magnesium 23 undergoing beta plus or beta positive. Zero plus 23, 1 plus 11, and I forget what that is. What's atomic number 11? Sodium. Plus something else. Luke, what else we got there? The V thing, yeah. This time we've got a neutrino produced. Yeah, I don't know. I don't know where that comes from. Now we got to kind of work backwards here. We're not told what type of radioactivity is, but that's okay. We go through the same process in balancing out the mass number and atomic number. Phosphorus 30 goes to sulfur 30 plus what? 30 plus 0 equals 30. 16 plus negative 1 gives me 15. That's a beta particle. We also have an anti-neutrino produced there. 234 plus what equals 238? Matt B, that is. 234 plus what equals 238? Right? 90 plus what equals 92? 2. So 4,2 is going to be 4,2 alpha, or you could say 4,2 helium. Doesn't really matter. And there's nothing else that goes along with that. No neutrino, no antineutrino. 13 plus 0, 6 plus 1, positive 1. That's a beta plus or a positron. Plus what else? This is a neutrino. That's the little v without the arrow, or without the line on top of it. I got one more example for you. Number 5. This is what we call artificial transmutation. This is not radioactivity. This is something that we're doing. In the first case, A, we're bombarding a nitrogen nucleus with an alpha particle. So we're firing alpha at nitrogen. We're colliding these two together. They fuse together briefly and then split apart into oxygen 17 and what else? Well, 14 plus 4 is 18. 7 plus 2 is 9. So we got to get 18, 9 on the right side. 17 plus 1 equals 18. 1 plus 1 equals 9. What is that? It's hydrogen. Yeah, it's hydrogen. Or you could have said 1, 1. It's a proton, right? 1 proton, 0 neutrons is a proton. Or a hydrogen nucleus, whatever works for you. Both would be correct. This is something called electron capture that is, it does have a special name associated with it, this one. But it's not something that we have to be familiar with other than, like any other equation, being able to balance them. Here, the cadmium nucleus absorbs a beta particle, absorbs an electron, and then it gets converted to something else. 105 plus 0 gives me 105. 48 plus minus 1 is 47, and that's going to be silver. Now, just because you have a beta particle there does not mean you add an antineutrino, because this is not beta decay. Beta decay has a beta particle on the right-hand side, not the left-hand side. So my product, or my parent, is cadmium. My daughter is silver. I'd like you to take a look for the next 6 minutes at worksheet number 24, please. There is one typo with this, although it shouldn't affect you too much. Question number 2, it says 222.86. It should say Rn, but really you're not using the chemical or the symbol of the element to determine what the numbers are anyways, right? So you would have, didn't really matter that you didn't know what that was. Let's take a look at number 6 before we move on here. It says lead 208 plus something goes to HS, I'm not even sure what that is, plus a neutron. So what do we got here? On the right-hand side, we've got 265 and 1 is 266. 108 and 0 gives me 108. So let's get the total mass number and the total atomic number on the one side that we know everything for. And then let's say on the other side, it's got to add up to give me those numbers. 208 plus what gives me 266? Spencer, what would that be? 58. And 82 plus 26 gives me 108. Now, what's atomic number 26? I think it's iron, isn't it? Fe. Of course, we've got our periodic table. If I was writing a test, I wouldn't rely on my memory because most of the elements I don't remember. I've got my periodic table, so I can always check. Atomic number 26 is iron. Good? Make sense? Like those, a question like that's a little bit harder than a question like number 5 or number 4, right? Because you've got two things on both sides. Just make sure the total mass number balances out with the total mass number on the other side. The total atomic number balances out with the total atomic number on the other side. Yeah? Question? Okay. No, because 265 and 1 is 266. Right? Yeah. That make sense? So those two add up to give me 266, and then those two add up to give me 266 as well.